In the vast silence of the cosmos, where distances grow so large that even light becomes a slow traveler, one truth governs everything. Nothing is permanent. Worlds rise, worlds fall, and the universe continues its patient march forward. But among all structures drifting through space, stars hold a unique authority. They illuminate galaxies, forge the atoms inside our bodies, and ultimately decide the fate of everything orbiting them. Yet every star, no matter how bright or powerful, begins from the same unremarkable place, an invisible cloud of gas and dust drifting aimlessly in the cold. This is where our story begins. Not with fire, not with light, but with stillness. A stillness waiting to collapse. Long before a star becomes a beacon in the sky, it exists as part of a nebula, a silent cloud spread across light years, cold enough to freeze memory itself. European space missions like Gaia and Euclid have captured glimpses of these structures, painting them as colorful artistic swirls. But the truth beneath those images is far more severe. These clouds are unstable, chaotic, and constantly shifting. Deep inside them, gravity performs its slow, relentless work. It doesn't shout, it doesn't rush, it simply pulls. Fragment by fragment, molecule by molecule, gravity draws the gas inward. As the cloud contracts, the temperature rises, pressure begins to build, and slowly an invisible center forms, a place where the rules start changing. For millions of years, this collapse continues. Nothing dramatic, nothing explosive, just a growing tension in the dark, tightening like a fist. Eventually, the core becomes so dense that atoms cannot hold their distance any longer. Hydrogen begins to fuse, releasing energy that has only one direction to go, outwards. This is the ignition moment, the first breath of a new star. Not a gentle spark, a brutal, uncompromising reaction that floods the collapsing cloud with light and heat. The star stabilizes only when the outward push of nuclear fusion balances the inward pull of gravity. This is the beginning of its main sequence life, the phase during which it spends most of its existence. Our own sun is in this phase right now, a quiet example of cosmic equilibrium. It burns steadily, without drama, powering the evolution of life and the motion of planets. But stars are not identical. Their futures depend entirely on their mass at birth. Small stars burn slowly, giant stars burn violently, and medium-sized stars like our sun walk a fragile path between stability and collapse. Every star carries a built-in countdown, a silent expiry date encoded in its own core. The moment nuclear fusion begins, so does the clock. What happens next, their evolution, their decline, and their death, is shaped by this single factor, mass. And that is where the story becomes far more intense. A star's main sequence phase is often portrayed as calm, steady, predictable. That impression is misleading. Stability in the cosmos is never effortless. It is a constant negotiation, a delicate tug-of-war between the crushing force of gravity and the fierce outward pressure generated by nuclear fusion. Inside the star's core, hydrogen atoms are being fused relentlessly into helium. Every second, the star loses millions of tons of mass, converted directly into energy. Yet from a distance, it seems unchanging. That is the illusion stars create, a tranquil exterior masking a violent interior. Stars of different masses behave differently during this long middle chapter of their lives. Small stars, known as red dwarfs, burn fuel slowly, sometimes surviving for trillions of years, longer than the current age of the universe itself. Medium-sized stars, like our sun, maintain a measured pace, destined to shine for around 10 billion years. Massive stars, however, live fast and die dramatically. Their enormous mass demands an equally enormous fusion rate. They blaze intensely, consuming their fuel in a fraction of the time. What these stars all share, however, is the inevitability of evolution. Hydrogen, the simplest and most abundant element in the universe, is finite inside every stellar core. And the moment it begins to run out, the balance that holds the star stable starts to falter. This slow shift is subtle at first: temperature changes, structural adjustments, internal currents moving differently. But the star feels it. Deep within, the core begins collapsing under its own weight because helium cannot fuse as easily as hydrogen. The star responds by increasing pressure and temperature, desperately trying to maintain balance. In this phase, the star's outer layers react dramatically. They expand outward, cooling as they stretch, turning the star into something far larger and far redder than before. This is the birth of a red giant. For European observers using instruments like ESA's Gaia or the Very Large Telescope, red giants are unmistakable: swollen, glowing, deceptively calm. But their calmness is a disguise. Inside them, the star is in the middle of a crisis, a core collapsing under gravity and an outer shell expanding in an attempt to survive. The internal structure becomes layered, almost geological. Hydrogen still fuses in a shell around the core, while helium sits at the center, waiting. Eventually, the core becomes hot enough for helium to begin fusing into heavier elements, such as carbon and oxygen. This marks the next stage in the star's evolution, another brief period of balance, another temporary victory over collapse. But temporary is the key word. Helium is far scarcer than hydrogen. When it finally runs out, the star will face a far more brutal reckoning. The battle between gravity and pressure shifts violently in gravity's favor. What happens next depends entirely on the star's size. For medium-sized stars, the kind that build worlds like ours, the end is dramatic but not catastrophic. For massive stars, the end is catastrophic by design. Stars are not eternal engines, they are finite machines. And the moment the last reserves of fuel begin to diminish, the universe starts preparing their final chapter. A chapter that determines whether they fade gently into the dark or explode with enough power to reshape entire regions of space. The main sequence is the calm before the storm. The red giant phase is the first sign of collapse. What comes next is unstoppable. When a star exhausts the hydrogen in its core, the universe forces it into a crossroads. The outward pressure that once balanced gravity begins to fail, setting off a chain reaction that exposes the true nature of the star. Its future no longer resembles its past. This is the point where stars separate into two groups: those that die quietly and those that die as cosmic catastrophes. For medium-sized stars, the ones comparable to our Sun, the red giant phase marks the beginning of their decline. But for massive stars, what follows is the most violent transformation in the universe. Let's start with the giants that end gently. The fate of medium stars, a controlled collapse. When a sun-like star becomes a red giant, it has already expanded far beyond its original boundaries. Its outer layers become fragile, loosely held, vulnerable to the slightest instability. Inside, the core contracts, heating until helium fusion ignites. This is called the helium flash, a brief but intense event that stabilizes the star for a limited time. During this stage, the core converts helium into carbon and oxygen. But once these elements accumulate, the star faces a problem it cannot solve. The temperature required to fuse carbon is far beyond what a medium star can produce. Its internal pressure is simply not enough. So, the inevitable begins. The inner core collapses further, but the outer layers can no longer stay attached. They detach gradually, floating into space like layers of smoke peeling away from a dying flame. This process forms what astronomers call a planetary nebula, a luminous shell of gas expanding outward, shaped by stellar winds and ultraviolet radiation. Despite its beauty, it is essentially the star's discarded body. At the center lies a dense remnant, a white dwarf. A white dwarf is no ordinary object. It is the compressed heart of a once living star, crammed into a volume no larger than Earth, yet containing mass comparable to the Sun. Its gravity is extreme, its temperature blistering, and its lifespan unimaginably long. It will cool, fade, and eventually become a cold, inert black dwarf, a stage the universe is still too young to witness. This is the gentle ending, a quiet surrender to gravity. But the universe does not treat all stars with such restraint. The fate of massive stars: fuel, fury, and instability. Massive stars burn through their hydrogen quickly, racing through their life stages at breakneck speed. Once they leave the main sequence, they expand into supergiants, colossal structures many times larger than the Sun, glowing with raw intensity. Their internal story is entirely different. Unlike medium stars, they can fuse heavier elements, and they do so rapidly. Helium becomes carbon, carbon becomes oxygen, oxygen becomes neon, then silicon. Each stage becomes shorter, faster, more unstable, until one day the core begins producing iron. Iron is the final barrier, the point of no return. Fusion of iron does not release energy, it consumes it. For the star, this is equivalent to slamming into a wall at full speed. The outward pressure collapses almost instantly. Gravity wins completely. The core implodes. This implosion happens in milliseconds. The core shrinks to the size of a city, densities rise to unimaginable levels, and then, just as quickly, the collapse rebounds. The shockwave slams into the star's outer layers, tearing them apart. This is the birth of a supernova, the brightest, most destructive event a single star can produce. For a brief moment, a supernova can outshine an entire galaxy. Its blast waves travel across space, creating new nebulae and scattering elements heavier than iron, gold, uranium, plutonium into the cosmic medium. These elements will one day form planets, oceans, and life. But what remains at the center of the explosion is even more extraordinary. The remnants of a titan, neutron stars, and beyond. When the collapsing core is halted by nuclear forces, it forms a neutron star, an object so dense that a teaspoon of its material would weigh as much as the tallest mountains on Earth. These remnants rotate at terrifying speeds, emit powerful magnetic fields, and sometimes become pulsars, sending rhythmic beams of radiation across the cosmos. But if the original star was even larger, far beyond the threshold of stability, the collapse does not stop. Nothing stops it. The core continues shrinking until space itself curves inward and light can no longer escape. This is the birth of a black hole, a region of space where gravity becomes absolute, where time slows, where the laws of physics dissolve into uncertainty. And it all begins with a massive star running out of fuel. Mass determines everything. It decides whether a star becomes a sculpture of fading light or a gravitational wound in space-time itself. But the story of stellar death doesn't end with the collapse. Because what stars leave behind, their ashes, their shockwaves, their energy, becomes the raw material for the next generation of cosmic structures. The universe recycles everything. When a star dies, its story does not end. Instead, the universe begins to reshape the pieces it left behind. In the aftermath of stellar death, whether through gentle shedding or through catastrophic explosion, new structures form, new chemistry begins, and new generations of stars slowly emerge. This recycling is not poetic metaphor. It is the fundamental engine of cosmic evolution. A star's life is a cycle, and its death is the ignition point for countless futures. The ashes of a sun, quiet remnants. Medium-sized stars leave behind planetary nebulae, immense glowing shells of gas expanding outward, sculpted by radiation and stellar winds. Though they appear delicate, their structure is the result of intense internal forces. These nebulae spread carbon, oxygen, nitrogen, and other elements into the interstellar medium. Over thousands of years, their gas thins out, merging with the larger molecular clouds drifting across the galaxy. The white dwarf at the center fades slowly, but the material it discarded becomes part of the next cosmic chapter. The dust grains forged inside its red giant phase eventually mix with interstellar clouds. These grains will one day form the building blocks of planets and organic molecules. It is a quiet contribution, but not a small one. Stars like our Sun are responsible for a substantial share of the elements that shape rocky worlds and biological life. The ashes of giants, violent creativity. Massive stars leave behind something far more dramatic. A supernova shockwave travels at millions of kilometers per hour, plowing through surrounding gas, compressing, heating, and stirring vast clouds. The explosion does not simply destroy, it creates. It seeds its environment with metals, with complex nuclei, with the rarest elements in the universe. Every atom of gold on Earth, every atom of silver in jewelry, every trace of iodine in the human body, all were formed in the violent furnaces of supernovae. Without these explosions, the periodic table would be half empty, and life as we know it would never have emerged. The supernova remnant expands for thousands of years, eventually cooling into sprawling structures visible in telescopes. The Crab Nebula, the Veil Nebula, Cassiopeia A. These are not just astronomical objects. They are the archaeological remains of destroyed stars, marking where a giant once stood. Inside the heart of such a remnant lies the core's final product, a neutron star, a pulsar, or a black hole. These remnants do not merely exist, they reshape their surroundings. Pulsars blast beams of radiation across space, sweeping like cosmic lighthouses. Neutron stars distort magnetic fields so intensely that matter can only exist in exotic, compressed forms. Black holes warp space-time itself, dragging gas into whirling accretion disks, launching jets that travel for thousands of light years. Stellar death is not passive. It is active, transformative, a trigger for new cosmic events. The birth of new stars, triggered by destruction. The enormous pressure wave of a supernova can compress nearby gas clouds, pushing them past the threshold needed for gravitational collapse. In other words, the death of one massive star can set off the birth of dozens more. This is how galaxies sustain themselves. They convert old stars into new ones through a mixture of destruction and renewal. The Milky Way, like other galaxies observed by European missions such as Gaia and Herschel, cycles its material endlessly. Roughly every few million years, a new generation of stars begins forming from the remains of the old. This recycling is the reason our galaxy still glows. It is why spiral arms shimmer with bright blue clusters, the signature of newly formed stars emerging from dusty cradles. The hidden link between stars and life. It's easy to forget the connection between stellar death and biology, but it's impossible to ignore once understood. Every living organism on Earth, every structure in human civilization, is made of elements forged inside stars. Calcium in bones, iron in blood, carbon in cells, oxygen in every breath. These atoms were not born on Earth. They were manufactured billions of years before the planet existed, in the cores of ancient stars, many of which died long before the Sun formed. When those stars exploded, they launched their elements into the galaxy. This material traveled through space, drifted into a growing molecular cloud, and eventually became part of the solar system. In a real sense, humans are the recycled dust of dead stars, the literal ashes of long-gone giants. The cosmic memory. A star's death may feel like an ending, but the universe treats it as raw material. Nothing is wasted. Everything is transformed. Even the darkest remnants, black holes, contribute to structure, shaping the motion of stars, clustering galaxies, and sculpting the gravitational architecture of the cosmos. In the vast timeline of the universe, stellar death is not tragedy. It is transition. It is continuity.
It is the mechanism through which the cosmos renews itself. But the final chapter of our story is not about the death of stars. It is about what the universe becomes when the stars are gone, a fate that awaits even the brightest galaxies.
Stars are the architects of the universe, but even they cannot escape the inevitability of time. Their lives, measured in millions or billions of years, are brief in the context of cosmic eternity. Eventually, the universe will witness the gradual fading of all stellar light, leaving only remnants, white dwarfs, neutron stars, and black holes scattered across the cold, expanding void. White dwarfs, fading beacons. Medium-sized stars, after passing through the red giant and planetary nebula phases, leave behind white dwarfs. For billions of years, these dense objects radiate leftover heat into space. Slowly, imperceptibly, they cool. As the universe ages, white dwarfs will dim into black dwarfs, cold, inert spheres of matter, no longer producing energy, but still containing mass and memory of their stellar life. In this sense, even silent death has lasting consequence. Neutron stars and black holes, relics of fury. Massive stars end their lives in supernovae, leaving behind neutron stars or black holes. Neutron stars, spinning rapidly and emitting beams of radiation, will gradually lose rotational energy, their magnetic fields slowly decaying over trillions of years. Black holes, however, are more enigmatic. They remain for incomprehensibly long times, distorting space-time, trapping light, and occasionally merging in cataclysmic collisions that send gravitational ripples across the cosmos. Over unimaginable timescales, even black holes are not eternal. According to modern physics, they slowly evaporate through Hawking radiation, releasing their remaining energy into the universe before vanishing entirely. Even the mightiest remnants of stellar death will eventually fade into nothingness. The big picture: stellar life as cosmic recycling. The life cycle of stars, birth, balance, collapse, and death, is the engine that drives chemical complexity and structure in the universe. Each generation of stars produces elements, seeds new stellar generations, and sculpts galaxies. The supernovae, the planetary nebulae, the dispersed gas clouds, all these processes create the cosmic scaffolding on which future stars, planets, and even life itself may emerge. It is in this cycle that humanity finds its origin story. Every atom in our bodies, every grain of matter on Earth, is the product of countless stellar generations. The stars that lived and died billions of years ago provided the raw ingredients for everything we know. The end of light. Looking far ahead, beyond trillions of years, the universe will grow dark. Hydrogen will be depleted. Stars will no longer ignite. Galaxies will drift apart as cosmic expansion accelerates, leaving black holes and cold remnants scattered across an ever-increasing void. This is the universe's quiet, inevitable finale, the stellar era giving way to the degenerate era. Yet even in this darkness, the echoes of stellar life persist. The elements forged, the planets formed, the life sparked, all are reminders of the star's extraordinary influence. Even as light fades, the memory of stellar processes endures in the matter, the structure, and the very fabric of space-time. Conclusion: the eternal cycle. The life and death of stars are not just astronomical phenomenon. They are a testament to the cosmos' relentless creativity and indifference, its capacity to destroy and create in equal measure. Stars are ephemeral, yet their impact is eternal. They illuminate galaxies, forge the elements, and trigger the birth of future generations. In a universe without sentiment, their legacy is the most profound proof of continuity. For observers in Europe and across the globe, every twinkling star is a message from the distant past. It tells us that life, matter, and energy are perpetually recycled, that endings are beginnings in disguise,
and that the cosmos is far grander, older, and more intricate than we can ever fully comprehend. From the quiet collapse of a nebula to the violent explosion of a supernova, from the delicate glow of a planetary nebula to the inescapable gravity of a black hole, stars are both storytellers and sculptors. Their lives span eons, their deaths echo across galaxies, and through them, the universe continues its unending rhythm, creation, destruction, and transformation, forever written in the light of stars. And so, the story comes full circle. Every atom, every molecule, every life that emerges is bound to this stellar history. In the life and death of stars, we see the ultimate truth of the universe, that from chaos comes order, from destruction comes creation, and through it all, the cosmos perseveres.